Welcome to another HVAC Engineering-Techie training video. Today's lesson is on DDC control installation and wiring. You know, if you design the system correctly and you have the correct sequences, but if you install it poorly, you're still not going to have a good working system. So installation is important, and how it's wired and what kind of wire you use is very important to the system. Remember, HVAC Engineering-Techie channel is a channel that talks all things HVAC. Engineering design, construction, equipment, systems, test and balance, controls, efficiency, and performance. So, again, I'd like to ask you to become a subscribing member if you're not already by hitting the subscribe button down below. Give me a thumbs up if you like the videos. It keeps me on the air with Google, and I really appreciate it. Costs you absolutely nothing, and it's painless. No one will bug you, but it really helps me. I appreciate it. Alrighty, let's get started on controlled wiring. All right, to start, we're just going to kind of review the general control video offerings we have, so you'll kind of get a full review of what's available. So available is C1, which is the basics, which hopefully you've already watched. C2 is controlled network devices, what devices are networked together. C3 is DDC control architectures, what are the different LAN architectures. C4 is control components and devices, and of course this is how to wire them up. C6 is water-cooled central plant sequences. 7 is hot water plant sequences. 8 is chill water plant sequences. 9 is VAV air handler controlled sequences. C10 is air handler VAV air handler sequences. C11 is outside air handler controlled sequences. C12 is tuning DC loops, which is important. C13 is how to select and size control valves. C14 is how to select and size control dampers. C15 is how to do pneumatic controls. So that's the entire breadth of them, and I know that we don't do pneumatics much anymore, but we still do, and there are some things that you need to know. Alrighty, let's get started on down the line here. Alright, control network wiring. Now, if you've already done the architecture system, you'll understand what all these are. But if you have a wide area network, which is wired up here, which is the owner's system, it is almost wired with Cat 5e or Cat 6 up here at the top, and that's a wire designation. So it's a wire you buy that meets the specification of Cat 5e or Cat 6. That's how those are all wired, and normally it's in a cable tray. And these don't belong to you; these belong to the owner. And my strict advice is to never put a cable in a cable tray. It seems like it'd be the place to go, but the problem is that the data cable people own that tray, and if they find a foreign cable in it, they normally just cut it out. So you don't want to do that, because they keep track of their cables very closely, and you don't want to have a damaged cable. So now our LAN's down here, regular LAN, and that's the local area network, and that's the wire that we as control contractors install, and that's normally a Cat 5e cable, normally free air cable or in conduit. It depends on how it's specified. If the engineer wants the LAN in conduit, then it'll have to be in conduit. Otherwise, it's free air cable, and we'll talk about how those are installed. Now, down below we have these buses, and normally these buses are twisted pair shielded cable, normally free air cable or in conduit, depending on where it's going. If it's going to something that's exposed, like a chiller plant or an outdoor chiller or an outdoor air handler, then it'll be in conduit. Otherwise, if it's in the ceiling space, it may actually be free air cable. Now, these may also be LAN. Traditionally, we use these buses. By buses, meaning it's wire that carries a voltage signal. If it's a LAN, it carries what we call packet signal. It's a little complicated, but we talk about that in the architecture section. So this may actually be an IP LAN or an Ethernet LAN. And if it's Ethernet, it'll be Cat 5e cable, not twisted pair. But if it's a bus, it'll be twisted pair. And the functionality down here doesn't change depending on what the wire type. And what kind of wire this actually uses, what kind of LAN, if this is a LAN or if it's a bus, is all based upon the manufacturer. What does he provide? And so you have to know, see the cut sheets of your manufacturing product to make sure you know what kind of buses and wires these go down here. So that's it, Cat 5e for these up here, twisted pair shielded, or Cat 5e down here. Now, Cat 5e cable Yes, normally we use a Belden, but you use a Belden equivalent or whatever, and a Belden's a wire manufacturer, but it's done on an IEEE standard. And a Cat 5, Cat 5e, Cat 6 cable is a cable with twisted paired non-shielded wire. And it normally has 6 conductors, 5, but 6 conductors, and those conductors carry different parts of the signal that it needs to do that LAN. And many people buy them that are pre-configured. In other words, they already have the jacks, RJ jacks on the end of them. But normally, as control contractors, we normally install the jack. Now, what's really important about how you install those RJ jacks on it is what the wire configuration is, and you'll have to understand the tip and ring of the wire, and you'll need to learn how to do that to make sure that you always have the correct wire colors on the correct pin of the jack, or else nothing's going to work. And most control contractors carry testers that allow them to plug in the wire to make sure their jacks are good and they're correctly pinned. All right, so now this is a diagram of a controller, and this happened to be a job I did a design review on did a submittal review on the other day, and I thought, man, this control contractor really did a great job on his submittal, so I lifted his submittal page because it did such a great job. This is really a well laid out diagram. It shows the field guy how to wire every single thing. If you notice real carefully, these are all color coded. So it says on this one we're going to use a black wire, and it shows what color wire. The red wire is here, the black wire is here, and these are crimps actually. And these are the wires coming from this actuator. And so this is a damper, and it shows what wires to leave open, not to wire. So this is a completely great diagram. This shows the installer. I mean, this contractor's learned to not leave it to chance. Don't leave it to a field guy to make up his mind how he's going to wire these, because he'll do it wrong. And that's a problem. So by having the drawing, if he makes a mistake, it means because he didn't follow the drawing, and we need to do that. So anyway, these are the inputs and the outputs for this device. So this is the wiring diagram for that. So what happens here, here's the inputs, normally a twisted pair, shielded cable, normally free air, or it might be in conduit. So if these are sensors out here, which I think they are, they're coming in with a twisted pair, and they come to a point on the controller. And this is how they're wired. So they're normally free air cable, and we'll talk about that in a little bit. And then this is on the control side, and this output's normally twisted pair cable, normally free air cable or in conduit. Or if it's like going to a relay and it's digital, starts off, it's not analog, it may be a 14 gauge THHN wire. So it may just be a regular copper wire insulated with PVC. But depends. If you have an actuator or something, it will be a cable. It'll have 2 or 3 conductors twisted inside and won't have a shield. If it's an actuator, it won't have a shield. But if it's something like a transducer, it might have a shield. But normally it's free air cable, unless these are all exposed in a mechanical room or something. Then it might be all conduit. This particular controller, this is where the 24 volt power to power this controller comes in. And depending on the type of devices inside this controller, like it has triacs for relays. Triacs, a electronic relay. It doesn't actually have points that click. It actually is electronic. It's a discrete device. And it doesn't take many amps. And it can actually be driven. The driving power for the device can actually come through the controller. Now, if you have a device that takes a little more power, then this particular control manufacturer does something nice. It provides I/O devices that are not loop powered. Then they have separate power. And this one happens to be 24 VAC, and this one down here is 24 DC. So if you have a device that needs DC power, you can actually just get it right here. You don't need a separate DC power supply, as long as the current from the controller is greater than the current the device is using. And you have to look at the cut sheet for the controller to make sure you're not trying to drive a device that takes more current than this device will provide. If you do, then you have to have a separate, if it's VAC, if it's volt AC current, 24 volt AC, then you have to have a separate transformer to put power to this device. Or if it takes a DC power and it's greater than this device, then you have to have a separate DC power supply. But that's that, and so this will let you run power wires. And for these devices, the power is powered by the same gauge wire that you would for a control. So it's probably 18 gauge. All right, so this is a typical quality control panel drawing. It kind of shows you what they should look like. Now, not exactly, but in general terms, what they should look like. So remember, this is the panel ring, and this is what you would send out to the job site and have it mounted first thing. First thing on the job site you would do is come in and mount these panels in the right location where they are so that the electrical contractor can put his conduits into it, or the control contractor can put tubing into it, or whatever. So all your field devices activities can happen without the guts of this panel being there, because these things are fragile. And if you put these things on a job site open to sheetrock dust and debris, or people running into it with a scaffold or whatever, this is very fragile. So you want to keep those away until you're ready to start the system up and you have security, lockable control panels. That's another thing, is you don't want to leave your control panels accessible to everybody when you're not there. So we have locks on these, and we will lock them up and not let other people into those panels until we're there with them. So now this is some devices inside the panel. So here's some major devices. We have controller. This is the master controller, and these are the I/O devices. These may be transducers or power supplies, whatever these might be. These may be relays down here or whatever. And you put them inside the panel, and you run wire gutters around this panel so that when the control cables are coming in, they come into the wire gutters and they run around, and they go to the device. It keeps the panel clean and neat and seeing what's happening. Now, this is one of the most important things, is the power to a panel. And 90% of control contractors do this wrong. And unfortunately, the city inspectors don't know the code or don't bother with the code to actually tell them. The code says you cannot mix voltages within the same containment area. So you can't have 120 volt, 277 volt, 208 volt, or 24 volt in the same containment. So everything down here is low voltage, 24 volt AC or DC. And it doesn't matter if AC, DC, we can put them in the same panel. But we can't put 120 volt in that panel. So some panel manufacturers make a panel that has a little metal box up here for all the power to be in, but normally not. So what I'd always like to do is install a transformer that has a conduit connection on it, flex it to the bulkhead fitting on the panel, bring your 124 volt into this transformer, and then it comes out 24 volt on the other side. It's fine. So that flexible conduit is, as long as it's metal, is a divider. So we have now the 124 volt, and what a lot of contractors do wrong is they mount their transformer down here. They bring 124 volt into the gutters to that, and that's against code. Not only is it against code, it doesn't make good practical sense, because 124 volt or 277 volt or 240 volt actually has RF and spreads it around the panel. And if you have a set of conductors coming in for an input sensor, you could actually put noise on your system and have problems with your panel. So you don't want to do that. And I don't know why they don't follow the code. It just drives me crazy, to tell you the truth. So that's what happens. And of course, these are pneumatic tubes. Normally these would be copper, a 1/4 inch copper, or 3/8 copper, but normally 1/4 inch. They would come into a pressure transducer that can take this pressure, turn it into a DD signal, and run it up to this controller. So these are the things that's good. Now here's something that's important, is wire tags. Wire tags everywhere. Wire tags are very, very important, because it is very difficult for an operator to tell exactly which wire goes where. And if he doesn't know that and he's got to troubleshoot something, it becomes very difficult, especially if they're all the same colored wire. Say they're all white. You know, they're all multi-conductor coming in, and their cable, and they're all white exteriors on them. You can't tell the difference unless the wire tag. Now, what else should be in the panel on the cover is there should be a diagram of what this thing is controlling, so that an operator can look and see right here what he's looking at, and then there should be a wire tag list. So there's two ways to do wire tags. One is to actually put the name of the device. So let's say this is a relay and it's going out to a damper or some switch. They would put the actual name of that device so you can tell what it is. Well, the problem is you may only have an inch here, and that it may take more, so you don't have room. So normally the default then is to put a number. And we put a number down here on it, like this might be, all ones may be inputs, be 1, 2, 4, 125, 126, or whatever. And then the outputs may be another set of numbers, or they just may all be sequentially numbers. But over here should be a list. This should be the index. And the index would say that, okay, so here's the numbers, the wire tag, and here's exactly what it is. So now everyone knows what it is. Now these should be laminated and then glued to the panel so they can't be removed, and that they will last a long, long time. So that's a general panel. It tells you how these conduits can come into the panel. Now, it doesn't matter to us whether they come into the top or the bottom normally, but the only thing that is important is don't mix cable types. Don't mix input sensors and output wires to the same conduit or the same area. You need to separate those just to be safe, so that there's never any chance of any RF signal coming in on an input. Output RF coming in on an output actually can come into a controller, but it's got to be pretty serious to do that. All right, so also remember, if you take in the component section, actually these panels come with a back plane, and this back plane actually unbolts. So what we normally do is we install these rings. We take the back panel and we take it to the shop, and we install all this stuff on the shop. We don't terminate the wires, but we install the gutters, we install the controller, we install all this. We bring it to the site and install it in the panel, and then we wire it up. So that's kind of the process. So here's a typical controller, like say a VAV box controller. And if it's in a plenum area and this is not plenum rated, then it needs to be in a metal box. If it is a plenum rated controller, now what that means is that the plastic cover is fire rated. It doesn't generate smoke, and it's not a fire hazard. If it doesn't have that correct UL rating in the US, if it doesn't have the UL rating, then you have to put it in a box. And so then you put your I/O wiring. So we have this again is the power coming in here. I'm sorry, this is I/O going in and out. This is also I/O going in and out. And this is a power coming in. And the way I like to do power on these was install the transformer with a bulkhead connector here on the low voltage side and the high voltage side into a J box. So you brought the conduit of power into this J box, wired the transformer up, and inside the can is we're not mixing voltages again. So also on our cable, when we have free air cable coming out of a panel, we need to secure those cables somewhat close to the panel. It's all done to try to prevent mechanical damage, someone running into the wire or something like that. So we don't want to do that. Remember, if this is a plenum and you've got this in a can, all this wire must be plenum rated. All the wire ties must be plenum rated. That's really important because an inspector may catch you on that, and you don't want to be caught when you're halfway done with a job and have to go replace all that stuff. That's very expensive. So you want to be right to start with. All right, so here's a unit mounted above a ceiling. This is either it's not a plenum, or all this stuff is plenum rated. And so it has the controller again, just like this one. But again, we have the conduit coming in. Probably have a fuses on this power coming in. And again, the code requires 120 volt being a conduit, but once we got a transformer, we can be free air to the controller. This is the LAN coming in, and it needs to be fastened sometime, and these are the I/O wires going out. And the one thing about it, when you've got a controller like this, you need to leave a little loop for some extra wire. So if we have to replace this, we can take it off and move it around a foot or two. It doesn't have to be very much, but a little bit. Never stress this to be tight. Now, the one thing about wiring sensors, they should never have a connection. a temperature sensor or a analog sensor coming in should go completely from the end device completely to the controller connection. If you have to bring it in and have it to, you can do it to a termination board on the panel or a marshalling panel. But that's extra expense. We don't normally ever do that. But you should never ever have a field splice. So what happens sometimes is a crew goes out and does a rough in, and they'll pull a bunch of cable and they don't give you enough cable to terminate it. It's too short. You can't have that. You got to make sure it's long enough. Give them a couple extra feet on the end. Yeah, it's a little waste of wire, but it's much better than have to replace the whole wire because it's too short. Wall-mounted control panels. Wall-mounted are normally done on unistrut or some kind of structural panel, and then we put unistrut and put the panel on that. Normally we use 3/8 bolts for that. And the only thing you have to be careful of, if this is exterior when it's open to weather, is that this panel has the right NEMA rating to be exposed to weather. And also you have to be also real critical to look at the back of the panel. Because most panels, 3R panels that are rain drip, have holes in the back of the panel, which means they're now violated. To do that, you have to have a solid plate back here to mount this on, so that solid plate prevents those holes from being open to weather. That's an experience kind of thing you got to check about. So, these are mounted exterior. If you mount them on a wall, no problem, because those holes are sealed. But if you mount them like this on a piece of structural steel, like under a cooling tower or something, you got to seal that back up, and normally you just use a plate on the back to do that. Okay, free air cable. Now, free air cable is just the cable you run, and if it's in a plenum, it needs to be plenum ready. If it's not a plenum, it doesn't matter. It can be regular cable. But you always run the cable. You need to attach it with J-hooks, or you can wire tie it right to a member, but always tie to a structural element as high in the structure as possible. Never attach to electrical conduit hanger rods, mechanical duct, or pipe, or mechanical hangers. And the reason is because your wire will get destroyed, because there's a lot of things, and some of those things move, like pipe. They actually move. You do not want your cable tied to it. And the reason we tie it to the highest part of the structure, it's the safest place to not have your wire destroyed. It's very important. So it's just try to get it out of the way so no one else knows it's there and has to bother to work about it. So that's what you do. You wire tie it up, or use what's called J-hooks, and the wire can sit in the J-hooks. J-hooks allows the wire to move. And wire ties, if you wire tie it up, you don't want to wire tie it really tight. You tighten it up, but enough that the wire still has some flex, so it can move a little bit within that hanger. Never lay control table and data cable trays. They will be removed or damaged by the data contractor. Now, I know that sounds like it doesn't make sense because that's what cable trays are for, but it's not your cable. And so you don't want to do that. Your cable will be different color than the data cable guy, and those cable trays belong to him, so you want to stay away from those. Even sometimes we've had people try to wire tie to the outside of the cable tray. Don't do it, because they'll still cut it out. It's very, very frustrating. Wire tie cable, and another thing about cabling contractors, many times they're in there after the contractor's done. So there's no one there to police what he does to your cables. So just be safe. Don't put them in a cable tray. Wire tie cable bundles together with a bundle twisted in a rigidity for a bundle. So if you have about 10 or 20 wires all going the same place, you want to twist them together and then tie the whole bunch off to secure it to a structure. And this gives it a nice, they're not loose, they're together, they stay together when they're twisted. And it makes a nice installation, an installation that will not be easily damaged. Label all control cable as to function at either end, remember. Normally we're blue for a control cable, but you need to check your job specs because they may have a specific color for your cables, and you'll need to adhere to that. But normally we use blue colored or specified color cables to the network LANs, or use blue painted J boxes or cables that are easily identified. What we're trying to do is make sure people can identify your cable, and so we can use colors to do that. All cables to be run parallel or perpendicular in structure. No point-to-point runs of wire. Remember, we're trying to keep these out of harm's way, and if you run point-to-point, Your wire is going to be damaged, so don't do that. All cables be run level or plumb to structure, kind of what I just said. Cable shall not be run diagonally from point to point that is not square to structure. Cable shall not be tied to ceiling support wires and shall not cross the ceiling tile area less than 36 inches above the tile. So if you run a cable low through the middle of a tile and someone has to access that, they're going to move your cable. And if it ain't long enough, it will get damaged. So you can't do that. You got to stay above the tile. Cable shall not be draped or laid on ceiling structures, light fixtures, transformers, or high voltage conduits, because you can pick up radio frequency, and that can be a problem for your communication. Wall sensors drops shall be run in conduit as shown. In other words, so if you've got a wall thermostat and you're going to run a cable down to it, the gold standard is to put a J-box in the wall and run a conduit there so you can run it down there. Now, a lot of people just try to fish a cable down there. The problem is that later on, if they need to change something, that cable can be damaged trying to get it in and out. So conduit drops, especially in masonry walls, something like that, are the standard of how we normally do. Exposed cable should be run in conduit as shown. So in other words, let's say you got a vertical rise going up a building and it runs through a mechanical room or electrical room. So you down here your free air cable and up here your free air cable, but this is an exposed area. So what you'll do is run a conduit so all your cables are in conduit in the exposed room, but free air on either side. It's no big deal. Exposed cable exiting in utility room should run as follows. So if you've got a cable that you need to run free air cable out of an area in a mechanical room or in an area that is specified you can do so, then you need a J-box to get out of the conduit. Makes sense. All free air cable installed in return air plenums must be plenum-rated wire, plenum-rated ties, and plenum-rated connectors. That's really important. You don't want to make that mistake of use standard ties or standard wire, and an inspector finds out that it's not plenum-rated, you'll have to change it all. There's no other reason. It's no big deal. Just make sure you have that. In our trucks, when I was a control contractor, we only used plenum-rated ties, not wire, because that's more expensive, but with the ties and connectors were all plenum-rated. We didn't even let the guys have any standard ones. That made that safe. So conduit. Normally we use EMT, which is electrical conduit, for all indoor insulation and conduit. And they have connectors that different types. I mean, you can get these that are just, open with just a screw, or you get some that are liquid tight. I mean, not tight, but they have a threaded connector. And these are corner joints that allow you to be able to pull them. Use EMT or rigid when exposed outdoors or as specified. So EMT is intermediate conduit, and it's a little thicker than EMT, but not as thick as rigid. And they use connectors that are watertight, basically, and are used for EMT. This is an EMT connector. And rigid uses looks like water pipe. It's not. It's conduit, but it uses threaded connector just like a pipe. And your elbows are bent threaded pipe. So this is very thick conduit and is normally done for exterior exposed to weather. Use flexible conduits when attaching to a sprung piece of equipment. If you have equipment that is on springs to keep where vibration, then the electrical connection must also be able to flex. So if it's indoors and it's not exposed to weather, we use a metal flex like that. If it's outdoors, a liquid tight is a flexible conduit that has a coating on the outside that makes it weatherproof. Now there is a problem with these, is they'll last about 10 years. And if they're exposed to sun, the sun will actually eat this layer up. So they have to be managed or painted. Most people don't paint them, but that is a problem. Do not tie any control conduit to any other contractor's hangers unless approved by code and project management. That's actually a code requirement, but it also makes practical sense, because what happens is a contractor is responsible for his hanger system, and it may be a weight restriction. So if you start hanging stuff on somebody else's hanger, you may exceed their weight restriction, or it may have other problems, and it is definitely a code problem, so don't do that. All conduit shall be installed per project electrical specifications. Even if you're not bound to the electrical side of the contract, doesn't matter. You still have to follow that spec for conduit. And we use interduct for all fiber optic cables. And remember, interduct is a plastic conduit that has these ribs on it that only allow it a certain bend radius. And since fiber optic is very critical about bend radius because it breaks the fiber, we use this it won't allow it to bend enough to break a cable. All 120 volt or greater voltage power cables shall be run in conduit as specified by the specifications. Okay, wire terminations. Install power wires with termination connectors, or if you have a controller that has special terminal connections where you take off you pull out it has a screw connector, you unscrew it and stick the wire in it and screw it back, that's fine. That's the kind of connectors to have. But if not, if they have just ones where you'd have to stick a wire under a screw and tighten it down, without a special adapter for that, then you use wire ties. I mean, not wire ties. You use these kind of connectors. Use butt crimp connectors, never wire nuts. Never wire nuts and controls, because wire nuts can work off if there's a vibration source around. You want always crimps because they're a sure thing. And it can be the new modern crimps that are square. This is the traditional crimp. It doesn't really matter as long as it's crimp. Always ground controllers and metal control panels to power ground with green wire 14 gauge. So everything, you need to make sure your panel's grounded, because there's a whole bunch of things we have to ground in wire that come next. But we got to have a major ground to the panel itself. All terminations shall have as short of unsheathed wire as possible to retain wire pair twist. So inside the wires, like if you get a 18-2 shielded pair conductor, the wire inside that sheath is twisted, so the two are twisted together, and that has to do with managing the impedance within the cable. So you want to make sure that twist is retained when you peel back the outer cover so you can make a termination of the wires. What some guys do is they'll peel back a foot of cable, so give them lots, and then just leave those two wires loose, which eliminates the twist and gives you a possibility of getting radio frequency on those. So you don't want to do that. So you want to retain that as shortest connection as possible of the sheath, and we'll show you that here. So what this means is that termination with shield and drain wires should be grounded on one end only. We have on shielded incoming cables, which this is done for sensors or things coming in or analog input-output, and you'll see that they have this wire and they have a cable on the outside. They have a sheathing, and underneath that is a braided or aluminum foil shield. And this is just real light aluminum foil. So what happens is when you cut this cable, you peel back this shield, and then you peel back this foil. You don't take it off. You just peel it back, and then you expose the wires there, and so you got a power wire and a negative wire, and then you've got a shield, and the shield is just a steel or aluminum wire. And what you do is you wrap this shield around that wire, and then we normally tape the end to secure this shield to the ground. Now this shield wire, drain wire it's called, is what we actually ground. And we ground that drain wire. Now that shield is grounded. So any radio frequency coming in on this wire will actually go to ground and not bother this wire. So what I'm talking about, the twist, is the length of these wires. If you make this a foot or 16 inches long, we have now no longer twisted. These wires are twisted inside this cable. So we want to make sure they do this. Now the ground is only one end of the cable. So remember, this cable goes and has another end. But we only want to ground it on one cable. And the reason is it's called ground loop interference. What can happen is because grounds can have different, see how I explain this, they have different ground potential and actually have a possibility of running current from one ground to another ground. Now, this was discovered years and years ago, where we first had telegraph services in the United States, around the world actually. They put batteries in the stations, and what they did is they ran the signal over wire on telephone poles to go somewhere, and then they grounded the other side to just let it go through earth ground. and they would do the dashes. They run their telegraph across that way, and the Morse code. When they did all that. Well, they made this discovery that things working fine, but they realized their batteries are dead. But it's still working. Well, it's because there's a ground source. There's voltage in the earth. The Earth's got all this return current, so it's got current. And they was actually running these telegraph systems without batteries. They didn't need power because the Earth was providing the power. Well, that's kind of the problem here. So if you ground at one end and go 100 feet, 300 feet, and ground the other end, and if there's different potential in the ground at those stations, you may actually get some current going across that ground. It's called a ground loop. So don't do that. So you only do it on one end, and normally we do the controller end because it's convenient. Because we have a grounded panel, so we can just make that ground there. All terminations wired tagged for end sensor or device, so we put a tag on the wire to tell where that wire is going. So this is a poor what I was talking about. See, this person's, taking the casing off this wire probably for 4 or 5 inches because it was easier to do it, and there's the drain wire. And he's coming in. This is one of those connectors I was talking about that has a special connector. We loosen the screw and stick the bare wire in and tighten it back down. But if you have a connector like one of these, which has a screw to stick it under, it needs to be a connector like I showed. Now, these are the correct way. This is a poor wiring termination. It still worked, but it's not a good wiring practice because this can get you in trouble for quality. Now, one thing about when you have ground loops and stuff like that, they're really hard to figure out. So just make a habit of doing good wiring practice so they can't happen, so you can figure it out easier. So this one here is a bunch of digital outputs. So these are done in just THN wire. These are not control cables like these, the conductors. Now here we have one coming in, and you see this wire coming in. And this one happens to be this is a little confusing, but this one here is a sensor coming in. It's like a RJ7 connector. Normally it's RJ11, but this happens to be a bus coming in here. And you see these wires, these are coming in and connecting to this, and they're only about a ½ inch long. So this guy that installed this did a good job. There's very little room for twist. There's very little room for open area here. And he's taped them properly, and the shield is going into the ground. So these are good wire. These are I/O wirings, and these happens to be digital outputs, and these are THN wire. And you can't see them here, but these are a bunch of conductors, sensor wire with a twisted pair with a shield. And then these are wiring tags. This happens to be an industrial panel, but you'll see that they have all these connectors, and they have all these numbered wire tags telling where these wires go. I used to do industrial controls also, and I've had marshalling cabinets that have 400 red wires coming into them. You'd better have wire tags, because if you don't, trying to figure that out is hundreds of man hours. So wire tags are really, really important. And not only the tags are important, but the index is really, really important too. So that needs to be all documented for these wire tags. Okay, device terminations. Now, the control drawing I showed you early on, we looked at, the reason that's important is because the designer, the control contractor designer, he should have found the device he's going to use, got the cut sheets, and knows exactly what the wiring diagram looks like for each device. He puts that in the drawing so the field guy doesn't make a mistake, because there are a lot of different devices, and they may have different wiring terminations, wiring the way they're wired. So you must look at the device. So this happens to be a temperature sensor, and you'll notice this is a controller. And here's a black wire that's coming from the AI COM, and it's a negative COM. And then the AI out, this said red. It could be white, but red, and that is the plus signal. Now, remember that for DDC controlling, for digital, for DC, the color wires are different. You're probably used to 120 volt. Black is power and white is neutral. It's exactly opposite for DC. So you got to get used to that. If not, you're going to wire up a lot of things wrong, especially if you have two men on the same job, and one wires it right and the other's not used to it, wires it wrong, then you have real problems. So that's the truth. So this is a sensor, 2 wires, and a voltage coming. It uses voltage to tell what temperature it is. So this is a real easy way to connect. This happens to be a pressure transducer. This is a little more complicated. You can see it has the COM, black wire communication, going to the negative voltage, and then it has the A1, analog 1, and it's a pressure transducer, so it's an analog input, and it goes to the white one, the voltage. And then we have a separate voltage, and this happens to be coming in from a separate source. So this is a device that is not going to be run from the power is not coming in from the panel. It's coming in from a separate device. So this is a separate wire, and it has a ground over here. Now this is a double pole, double throw relay. In other words, and it's only being used for one pole. So this is the controller output. And you can see the COM is a black wire, and it's going to number 13. Now, number 13, you see, and number 14 is the coil that actually runs this relay. So we power that up, and here's the digital output, powered up 14. So it takes the power, and when this closes, this is a normally open relay. When it closes, it will then send power out to the load. So here's the load, and it could be 120 volt, or it could be 24 volt AC. But it comes in and goes to number 9, and you can see that number 9 is right here to this connector, and then we've got our output to number 5, so this is normally open. So when this relay closes, this moves over to here and connects the circuit between 9 and 5. So we've connected 9 to 5, and that rails it out. Now this is double throw, so we could also run another circuit off this side, but it would be opposite of this one. So if we're running it normally open, then this side would be normally closed. So, I mean, we could run both sides, but that's why it's important to show exactly what's going on so the field technician can figure out exactly how to wire these devices. And this is a motorized actuator. Now, most electric actuators are motorized. They do make some other magnetic ones, but I'm hoping those are pretty much a thing of the past. And it could be hydraulic ones are still motorized, so they have a motor in them. And what happens is inside the actuator, you'll see that this has a white wire and a red wire. And what these do, one drives it one way and one drives the motor the other way. It's a reversible motor. So one way opens the valve, one way closes the valve, unless it's spring return. And if it's spring return, then it just has two, and the spring will return it. But a regular motorized valve has two. So the switch coming in from the HVAC side comes into this, and then this switch, the controller switches it between point 1 and point 2. So now this does take 2 points to drive it open and drive it closed. If it's spring return, it only takes 1 point. So here's a floating point actuator. It's the same thing. It's the same valve, actually, but it has it's run slightly different. So in the controller, we burn 2 points, but what happens is the controller has a neutral point. So it says it's going to turn it on, and it'll drive it this way. And then when this point goes off, it doesn't do anything. It just sits there. So what happens, the valve, the actuator, will start to open and then stop and wait. And then if it needs to open more, this closes and it starts to open. Or if it needs to close, then it closes this point. Now it'll drive it closed. So this valve is either open or closed, not anywhere in between. This one here is like a modulator, but not quite. It opens, stops, waits, opens or closes, stops, waits. So it mimics modulation, but it is not modulation. This is a modulating actuator. And so this one has power to the actuator. So this could be 24 volt VAC, and it comes in black and it comes in hot. And then the controller has the digital point, so it's got a plus signal and a minus signal. And it actually, and this will be a different color because these might be the same conductor. So it will come out, and this gets the voltage signal that actually causes this actuator to modulate. Now, modulating actuators are a little different. They're still motorized, but what it does is it says, I need to be 50% open, and so this valve will drive until it's 50% open, then stop. And that's the difference between these motorized up here and this motorized modulating actuator. And that's why modulating actuators cost slightly more than a regular actuator. Because now modulating actuators can be spring return also. It just means when there's no power, they go to their normal state, whether it's normally open or normally closed, depends on the actuator. So these should be on the drawings and tell the installer exactly how to wire everything up. Okay, so now another problem control contractors have is wire drop, voltage drop. The code, the electrical code, NEC, spends a lot of time, a lot of effort telling you how to do power. But there's not a lot out there for 20-volt VAC. You have to actually calculate it all. Well, here's a table that kind of helps you do that. And understand, this is maximum amps for 24-volt VAC. So this is AC wiring. And you'll see that there is a 75C rating, and there's 90 degree C. These here are for, 90C is for power wiring in conduit. This up here is free air wire for power wiring free air. Like if you're going to run 24-volt AC to an 18-2 non-shielded pair to provide power for a controller. So this is how this works. Say you have an 18 gauge. This has 2% drop. This has 3% drop. Normally we recommend 2% drop, but in some cases you might push to 3%. But here we go. We have an 18 gauge and we have 25 foot of run. Now the run is the total length of wire, not out and back, but just from the controller to the device. And you'll see at 25 feet at 18 gauge with free air wire, we can run 0.6 amps is what we can run at 24 volt. If we had that same one in conduit, 18 gauge, it's 0.6 amps. So it's the same, didn't change at all. So now if you had a little longer, so these are not changing much. Let's go down here to if you want 3%, if you pushed it, you could go to 0.9. So it is a little bit different to do that. But anyway, these are the conduits, and these are 10 gauge wire, 12 gauge, 14, 16. So if you're running 24 volt power, or the 14 gauge, and you're going 25 feet, you could run 2.3 amps or 1.5 amps. So these are the amps that tell you, and these are conservative, but you don't want to have voltage drop. You need the voltage at the device. This will tell you how to do it. Here's 124 volt, which is basically the same. You can see this is in conduit. This is free air. You don't have many free air cables, actually. Most of it's only conduit. So if you had a number 12 wire and you wanted to go 100 feet, you could carry 5.8 amps in conduit if you had to, because it's 90 degrees C. Now, these little star symbol just means that the amp is limited by the NEC. The NEC has in a code down to these wire lengths starts limiting the number of amps. Even though if you do the calculation, it'll actually carry more amps, but NEC code has limited those. I don't think for controls you can be running much aught wire, but if you are, we do run 8 a lot of times. If we have a fairly big load, we can run that. So these are just kind of a helping hand to do that. Now remember, just stop the video and clip out that page, and you can have a copy of these tables. This is 277 volt, exactly the same thing. Say at 2%, you have a number 10 wire, 100 feet, you can run 21 amps. So it's telling you what's going on here. It's the same. Now both these power cables are for tables for copper conductor of not more than 3 power wires in a conduit. That's the rating of these amps. If you start getting a lot of power wires up to its maximum fill, the heat may start limiting the actual amps in the conduit. Wire colors. For the U.S., wire colors for 122.8 and 240 volt, all considered low voltage in the electrical world. L1 is black, L2 is red, L3 is blue, and the neutral is white, and the ground wire is green. That's the U.S. U.S. for 277 to 480 volt is brown for L1, orange for L2, yellow for L3, gray for the neutral, and green for the ground. In Canada, I didn't put it, but this is low voltage. This is at 120 to 240. The colors are the same. They just mix them up. L1 and L2 is reversed for color. A lot of people don't pay attention that each phase should have its own color. I mean, they have colors. They don't realize that L1 needs to be a special color. And for Canada, again, for the 277/40 volt. They swip the L1 and L2. I don't know why, but they do. They do all have white. So the colors are very common between Canada and U.S., but they flip around the phases. And here's DC power wiring. Remember, black is a ground wire, white is a power wire, and red is a power wire. So it's not like 120 volts, right? It's 120 volts. The neutral is white, and in this one it's black. So we got to remember that the colors are reversed for DC wire. Okay, so these are the conduit fill for control and power cables. So these are power cables, and these are the power cable size. This is the gauge of wire. And these are for THHN wire. They're for 40% maximum fill. And so this is the conduit size. So if you have like a 2-inch conduit over here, and you have, say, number 10 wire, it's going to be that amount. Will go on a 2-inch conduit. It's quite a few. So you could get those in there. This cable, the table over here, is much more valuable, and it's conductors. There's not a lot of data available what's conductors in. So this is a, and the reason is because if you have an 18-4 twisted pair, exactly how they're twisted is the area. And these cables are kind of lumpy because they got twisted wire in them. So it's a little hard to figure out what is the amount of fill for each different manufacturer's cable. Well, this is conservative enough to give you that is. So this is the maximum cable conductors in conduit. This is the conductor. So here's Cat 5e, here's Cat 6, and here's LAN or Cat 4. Here's twisted 22.2, 18.2, 18.4, 18.8. Here's PVC jacket, 18.2, 18.4. So you've got all these different cables. And then you got 18.2 plenum cable. Now, plenum cable is much harder to pull in a conduit than PVC. PVC slick. Whatever they do to a plenum-rated cable, it makes it hard to pull. It's sticky, kind of sticky on the outside. So here's the conduit size. So if you have a 1-inch conduit and you want to put some Cat 6 in there, you can only run 3 in a 1-inch conduit. Now, Cat 5e, you can run 6. You can tell that Cat 6 has extra wire in it. So they're a little thicker. So normally in a 1/2 inch, you can only run 2 5e, and normally you can only run 1 Cat 6. So now if you look here, if you have 1-inch conduit and you got 18.2 twisted pair, you can run 5 of those in a 1-inch. If you have a PVC jacket, 18.2, you can run 6. And again, if you have 18.2 plenum, you can run 6 again. So this is the fill for those conduits. These are based on cable with EMT conduit with a 31% fill. That's where we get the conservatives because these wires are lumpy. Use area calculations for mixed conduit fill. So if you're going to mix a bunch of different, which you can do, then you got to use a calculation. Applies both the EMT, PVC, and flex. Cable may be shielded or standard. So if it has shields or non-shielded, it makes no difference, still the number of wires. So this is a pretty handy table to have if you're an installer. So here's control devices. This happens to be a pipe pressure sensor. So what happens normally is we have a weld-a-let on the pipe or a half coupling welded to the pipe. We put a valve on that, and then we run copper tubing. And you want to, might be 3/8, but normally it's copper, a 1/4 inch. It can be copper, stainless steel, loop for vibration. So we want to put a vibration loop in here that keeps it in that way. Now, and then we come down to a valve block. And a valve block allows you, this is the sensor, it allows you to turn off and isolate this device from that pressure. And then you open this and you isolate both sides. So both sides have the same pressure. Now you can remove the controller. If you don't do that, you might actually expose the sensor in here to overpressure. These are real, if you have 150 PSI coming in here, and this had, whereas this was a different pressure on this side, say this was 150 and this was 100 PSI, or less, yeah, and then so this differential pressure sensor is reading around 50 PSI, and you come into this and you open this valve, and this is still at 150 psi, and you open this so that they can, if you disconnected this side, I'll get it straight here in a minute, you disconnect this side, now all of a sudden instead of 50 psi, this sees 150 psi, and maybe over the pressure rating of that controller. So we use these valve blocks to be able to remove and work on these without damaging the sensor. So this is a pipe pressure sensor. Now these are thermal wells or temperature sensors. And I would get control contractors who would tell me why there's not enough room to put the control well, the sensor well in the pipe. So I had to build a deal. So what they'll do is they'll come over here and if this is the pipe running here, they'll build a bunch of reducing couplings and have this well sitting way over here where the well doesn't even go into the pipe. The deal is the well needs to go at least to the center of the pipe. They make wells in even inch increments all the way to 94 inches, from 4 inches to 94 inches. So they make all kinds so they can do this. You have a big pipe, you can just put it in sideways and get to the center line. It could be a little over center line, doesn't matter, but it can't go to the other side of the pipe, and it can't be short. It's got to be the center line of the pipe because there might be laminar flow in the pipe where the liquids, each layer of liquid has a different temperature, and we're trying to read what the average of the pipe is. If you have a smaller pipe, well, you can put it in at 45 degrees and still get it in there if you can. If smaller than that, you can put it in a heel of an elbow like this, or you can put it in a T, elbow T, where the flow is going this direction, and the sensor is in the way. So there's no excuse of never getting a sensor in correctly if it's done correctly. This is the way to do a temperature sensor. All right, this is a duct sensor. Now, I've seen jobs, having been a commissioner for many years, I see jobs where the guy takes a bead sensor, just sticks it hanging free in the duct. That's not a proper installation. It should have a stainless steel probe. It should be bolted to the duct so it's secure. And if it's free air cable, if it's a conduit, you put it in a box. So you got a J box here and you conduit it. If not, it's free air, you tie this off somewhere close so this can't be damaged with this free cable. This is the one circumstance where you're okay to connect the cable to the duct because the sensor's in the duct. This is a low temp or an averaging temp in a duct system, and these are normally low temp and they're capillaries. Now, they do make them thermistor based, and if they're thermistor based, they can be installed differently. But why a capillary needs to be this way is because what we're trying to do is average. We want this sensor reading the average of this face area. Normally this is a coil, might be a filter, I don't really care what it is, but this is supposed to run horizontal through these square footages. So like if this, you can see these light lines are the square footage of the coil, runs through this, runs down here. And the reason this is important is these capillaries have refrigerant inside of them. And it knows the temperature by the pressure of the refrigerant. Well, it can't have liquid pockets in it. So if you run it, what some guys do, run it like this, means the refrigerant puddles down at the bottom and the temperature sensor is no longer accurate. Or I've seen them take it through a conduit in there and just wrap it around the conduit. That doesn't average anything. And really what I always laughed about is in every single sensor you buy comes a little cardboard box. And you pull out the sensor and there's a piece of paper in there. It's the instructions on how to install it. And of course, they take out the sensor, take the paper, throw it on the floor, and go install the sensor incorrectly. This is how it has to install. I get some complaints saying, well, I can only get a sensor in 20-foot length, and the coil is way bigger than that, so I can't do this. Well, then you do this. You know, you put as many as you need to get across that coil in every square foot, and if 20 foot's not long, 20 foot's a standard length. You can't, there's a few that make longer, but they're very rare. So 20 is normally what you got, and you just use more than one sensor, and you wire these in series. So that, you wire, both of these are temperatures, so they come back and they parallel them to get it to do that. All right, so this is valve connections. So if it's in conduit, it has to be flex conduit because the valve, they have to work on the valve. They may have to take it off, so you want a flexible connection so they get to that. If it's cable, then you run some flex cable. You run enough cable so that they can remove this actuator, and you just put some extra stuff in there. So now the valves need to be mounted with the actuator straight up. If it's in a vertical pipe, then it needs to be straight out at 90 degrees. Now, if you need to, this could lay over, but it has to be at least horizontal. Never put it down. And the reason for that is the actuator doesn't really care, but if the valve packing leaks, it'll destroy the actuator. So if you want to leak in, you want to leak in outside the valve, not leaking down on the actuator. So this should never be installed below horizontal. It should always be above horizontal. And that's installation of the valve. And if the mechanical contractor wants to install it upside down, you can't allow that. You have to tell them it has to be mounted differently. Dampers, if you have a damper with an over-the-shaft actuator side, and if it's free air cable, if it's conduit, then you'll wire it up to the conduit if it has a conduit connection. And if it's a linkage is mounted inside the duct, then you'll have to penetrate the duct and bring the cable into the actuator. Damper actuator torque loading. If you have to select the actuator, there's actually a separate video for this, but this is the easy way to do it. This is the damper torque loading. The reason this is kind of important to use this table because calculating a OBD is very, very difficult. It doesn't make sense because as this closes off, if the air is going this way, as this closes off, it's helping, the pressure here is helping close it, and the pressure here is trying to resist closing. They don't equal each other. It's a complicated calculation. So basically we use this. If it's 2 inch, 1,000 feet per minute, if it's parallel, no edge seals, parallel with edge sleeves, OBD with no edge seals, OBD with edge seals, and round. And this is the inch-pounds per square foot of torque for this kind of actuator at 2 inches. This is the same actuators at 3 inch, same actuators at 4 inch, or these velocities. And what you do is you take and you multiply the square footage of your damper time these factors to get the torque of the actuators. And these are standard actuator torques. Everybody makes approximately these ranges. Non-spring return, 9, 18, 45, 90, 180, 365, 100, 1400 inch-pounds per square foot. Inch-pounds. This is the actuator rating. So basically it's the torque equal to square foot times this factor, and you got to make sure you pick an actuator that's greater than this. So normally, most actuators we see are right around the 180 pounds. Some real small are 45 pounds, and I've never seen any down here, but 90 pounds, some make 95 pound, or 360. I don't think I remember ever installing a 1,400 pound. I guess they make them, but I don't know. The spring return are different, and that is because they have to, the motors in these have to overcome the spring. So that's a little bit different. And that's basically it for wiring standards and installation standards. I hope you have found this interesting and valuable to you. Have a great day. Appreciate you guys being here. And I'll catch you on the next one. Thanks.